In this lecture, we're going to talk about fragmentation pathways in mass spectrometry of alkyl halides, amines, ethers, and alcohols. First, let's look at alkyl halides. We have an alkyl chloride here, 2-chloro-2-methylbutane, and first we can see a couple of interesting things. One, we see this pattern that's typical of alkyl chlorides, where we have a peak and then a peak 2 more that's 1/3 the height. This corresponds to the natural abundance of the chlorine-35 and chlorine-37 isotopes, where one is 76% abundant and the other one is 24% abundant. So because of those two isotopes, we see one peak for chlorine-35 and another peak for chlorine-37. Now, if you were paying attention, though, you'll notice that the 91 peak does not correspond to the molecular weight of 2-chloro-2-methylbutane. When 2-chloro-2-methylbutane enters the mass spectrometer, it loses a non-bonding electron from chlorine. That creates our molecular ion, shown here. This has a mass-to-charge ratio of 106, which we don't see anywhere in our spectrum. And that's because the molecular ion quickly undergoes heterolysis to form this nice, stable, tertiary carbocation. When we have really stable fragments that can form, like this one here, then a lot of times we don't even see any of our molecular ion. So that explains the peak at 71. What then are the peaks at 77 and 91? If you're doing any math, the peak at 91 is loss of a methyl, and the peak at 77 is loss of an ethyl. These are formed when the molecular ion undergoes alpha cleavage to lose any of the groups that are attached next to it. So for example, it can have this ethyl group fall off, this methyl group, or this methyl group fall off. This slide shows how the alpha cleavage in alkyl halides works. The molecular ion can undergo cleavage to kick off a methyl radical, or it can undergo alpha cleavage to kick off an ethyl radical. And you can see that both of these are significant because we have that 91 peak and that 77 peak in our spectrum. Here again is the 91 peak, and here's that 77 peak. So those are both products of alpha cleavage. Alpha cleavage can also occur in amines. First, let's recall the nitrogen rule. Remember that if we have an odd number of nitrogens, we are going to have an odd molecular ion. So we see that happening here. We also see this peak at 86, and that's because we are undergoing alpha cleavage, or loss of a methyl. Amines do the same thing that chlorine does, where one of the non-bonding electrons is kicked off, and we end up with a radical on nitrogen in this case. And then it can undergo cleavage with any of the alpha groups. In this case, only methyl groups can undergo alpha cleavage because we only have methyl groups attached to this alpha carbon. We don't have any other groups attached to either of these carbons. This results in an iminium ion, which is very stable. It's stable because it's resonance stabilized, and you can draw a resonance structure where the positive charge is on the carbon. So we saw that alkyl halides and amines do have a significant alpha cleavage peak, but ethers do not. We don't really see the molecular ion here, but the alpha cleavage fragment is also very small over here at 87. Our base peak is this peak over here at 45. Let's quickly draw out what alpha cleavage would look like, just so we get a little bit of practice drawing out the mechanism. One of the non-bonding electrons would get kicked off, and we'd end up with a radical on the oxygen. And then one of our methyl groups would fall off, to create this species here, as well as methyl radical. And this is what corresponds with that peak at 87. Okay, let's look at alcohols. Here we have 1-pentanol, and 1-pentanol also has a molecular ion peak that we really can't see over here at 88. One of the significant peaks for 1-pentanol is this peak over here at 70, which represents loss of water. Let's look at how that happens. Again, one of the non-bonding electrons from oxygen is kicked off, and that can do in hydrogen atom abstraction from a hydrogen elsewhere in the molecule, causing water to be released. So this is the structure that corresponds with the peak over here at 70.